Good morning, students. So please type in the chat box. Am I audible? Yeah, so please type in the chat box. Is the audio and video clear to all of you? Yeah, it's clear, right? Okay. So in this lecture, we'll talk about potential flows. Basically, we'll try to introduce potential flows. But before that, we'll have a clear-cut view on simple flows. Basically, this Navier-Stokes equation we have solved. And we'll try to solve this Navier-Stokes equation for simple flows. Okay. I think the comments are not getting displayed. Just a minute. Yeah, can you all see the comments, right? I hope. Yeah, because there's a pop-up which is blocking the comments. Yeah, I hope it's clear. Correct. Great. So if you see, we have solved Navier-Stokes equation. So we'll apply this Navier-Stokes equation to certain simple flows again, like we have done in the last lecture for 𝐂𝐸𝐻 flow. Like we'll solve this Navier-Stokes equation for some simple flows like plain Poiseuille, 𝐂𝐸𝐻 flow, like in जो flow to pipes होता है. So after that we'll also see the boundary layer, and also we'll give a bit of introduction to turbulence actually. Okay, and all along the way we'll solve numericals. So if you go quickly to the last lecture, what happened? I think there's a big break in between, some 4 to 5 days. So we'll try to have a quick review of what we learned in the last lecture. So we have seen the Navier-Stokes equation. Navier-Stokes equation that rho x bar minus del p pressure gradient plus mu times del square operating on V is equal to density times rho dV by dt actually here. Okay, so this is the Navier-Stokes equation what we have seen in the last lecture. Okay, and this del square, we can see this is basically the Laplacian operator. Laplacian operator. Okay. So last class, yes. So in last class we have seen this for the 𝐂𝐸𝐻 flow. In today's class we will actually continue this simple flows. We will see 2 more flows, which is flow through pipes, basically 𝐂𝐸𝐻 flow, and also flow between 2 fixed plates. In case of 𝐂𝐸𝐻 flow, we have also seen that in case of 𝐂𝐸𝐻 flow, this is flow between a fixed and a moving plate. A fixed and a moving plate actually here. Okay, so this is between a fixed plate and a moving plate. Now if you see, we have understood if this is a fixed plate and here there is one more plate which is moving at u infinity, and let's suppose if this gap is h in this case, then if you take 1D flow, if the fluid particles are moving effectively in this particular direction, and if you call this coordinate system as this as x and this coordinate as y, then we have seen u by u infinity, the non-dimensionalized velocity is y by h plus alpha times of y by h into 1 minus y by h. So यहाँ तक सबको clear है? So एक बार type कीजिए chat box में. Are you all clear till this point? Like these are the points that we have seen in the last lectures. Okay, and I have shown you that after a bit of algebra, this is what you get. And alpha is called non-dimensional pressure gradient. Non-dimensional pressure gradient, and alpha is actually equal to h square by 2 mu u infinity into minus dp by dx is what we have seen. Correct? Clear? यहाँ तक सबको clear? If things are clear, then we will advance our analysis for the plain Poiseuille flow, which is flow between 2 fixed plates actually. Okay, now let's start this plain Poiseuille flow. After plain Poiseuille, I'll start flow through pipes, which is 𝐂𝐸𝐻 flow. Okay, so this is plain Poiseuille flow, which is flow between 2 fixed plates. Flow between 2 fixed plates actually. Okay, now this is flow between 2 fixed plates, I want you to understand some things, because there were previous year gate questions based on this topic, like if two plates are fixed, what could be the average velocity, what is the maximum velocity, these kind of things were there in the exam. So we will have a quick view of what is this plane Poiseuille flow. And if you see, if you fix two plates, for example, okay, so if you fix two plates, okay, these are two fixed plates, for example, here. Okay, now if these are two fixed plates, tell me one thing, whatever the flow happens here between the two fixed plates, that flow will be symmetric about this midline. Yes or no? Correct? Look, let us suppose if some flow is entering, then if the flow is entering and if these two are fixed plates, then whatever the type of flow that happens, of course we are doing only laminar flows, not the turbulent. So in case of laminar flows, what happens here will be symmetric about this line. Yes or no? Please type in the chat box. Can I say this? Because it's symmetric about this particular line. Correct? The complete physics is symmetric about this line. So what happens here, whatever the flow happens, that flow will be symmetric about this line. Right? Now, if you again establish the coordinate system, x, y, and maybe z is this direction, but effectively particles are moving only in the x direction. Okay, so this is the effective direction of the flow. Now, let us define a coordinate system. Let us take this gap as, for example, this gap as h and this gap as h. Okay, so this total spacing between the plates is 2h, so that this coordinate is y is equal to minus h and this coordinate is y is equal to h actually. Okay, to understand the flow, we should define a coordinate system, and that's the coordinate system. Now, if you apply continuity again, we already know that at any point velocity is actually ui plus vj plus wk, and also you have pressure field. So total you have 4 unknowns. So you need 4 equations for calculating, that 4 unknowns. So continuity, if you take dou u by dou x plus dou v by dou y plus dou w by dou z, because it's incompressible flow, we are talking about liquids in general, some water or oil is flowing, then clearly when the particles are moving only along x direction, can anyone tell me what are the values of v and w? Can anyone tell me what are these values? The flow is effectively happening in the x direction. So can anyone tell me what are these components of v and w here? What are these component values, v and w? The flow is actually taking place along x direction. Okay, and if the x component of velocity is defined as u, if there is no flow in the v and w or in the y and w directions, then what are the values of these components? Zeros, right? So v is 0 and w is also 0 actually. So this v is 0 and w is 0. And this gives you dou u by dou x is actually 0 in this case. Okay, and now if you look at the momentum equations, then you can see, like for example, body force I'm neglecting right away, no body force, because gravity is present but gravity is not driving this flow, so gravity you can neglect actually. Okay, so minus dou p by dou x plus mu times of dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square actually. Okay, and let us see one thing, the channel is sufficiently wide such that there is no variation along the z coordinate, so I am not writing z intentionally, because anyway you can see in this width of the channel, means the out of the board length is actually very large, such that there is no variation taking place in the z direction. Okay, now this is equal to rho into acceleration. So acceleration can be written as dou u by dou t plus u into dou u by dou x plus v into dou u by dou y. That's it. Okay, so nothing is changing in terms of z. Similarly, this is in x direction. In y direction, you can see minus dou p by dou y plus mu into del square v is equal to rho into dv by dt actually. Okay, don't get confused between this v and this v. Okay, this is a velocity vector and this small v is actually the y component of velocity. Clear? So don't get confused between those two. Now clearly v is 0, so whatever you apply, del square, Laplacian differentiation, whatever you apply, this is v, and this v is also 0. So this clearly gives you dou p by dou y is 0. What is the meaning of this? Pressure is not a function of y, correct? Because if something is not a function of y, then definitely, sir, does the flow fills the whole gap between the plates, or it's simple flow on one plate surface which is like pen channel? No, it actually fills the complete space. Okay, like you can see what we are analyzing is for this complete fluid flowing case. Clear? Okay, now let's see here, if dou p by dou y, if partial derivative of some function with respect to y is 0, that means there is no involvement of y in this function, correct? So therefore p is not a function of y, and clearly we know p is not a function of z because it's like a white channel, no variation. This implies pressure is only a function of x. Okay, pressure is only a function of x. Similarly here in this case, you can see this dou u by dou x square is 0 because dou u by dou x at any point is 0. If you differentiate this partially once again with respect to x, you will again get 0. Steady flow, we are not dealing any unsteady terms. This is again 0 from continuity. This v is 0. So from the first equation, you can understand minus dou p by dou x. Since pressure is only function, I can write this dou p by dou x as dp by dx. So minus dp by dx plus mu into velocity. Since u is actually function of x comma y, because we have made steady assumption, so no time, z direction there are no changes, so u is function of x comma y, but dou u by dou x is 0. That means u doesn't depend on x, u depends only on y. Okay, so if your u depends only on y, this can be written as d square u by dy square is equal to 0. Now clearly, as I have stated you in other sense, d square u by dy square is equal to, or mu times of d square u by dy square is equal to dp by dx. This is what you have here. Okay, simple math, nothing big, very complicated maths here. It's very simple. So just a bit of understanding of the different terms. Now one important thing, this is completely a function of y and this is completely a function of x, and these two are equal at any given point. That means this expressions should be equal to a constant, right? You remember in last class I was telling you this, if you have two different functions of different variables and if they are equal at any given point, then definitely they should be constants actually. Yes, I've told you this. You remember? Yes or no? That means this tells you the pressure gradient in the flow. The pressure gradient which is developed in the flow is actually a constant here in this case. Is this clear to all of you till this point? If it's clear, we'll solve this differential equation. It's a one-dimensional differential equation. We'll solve this and we'll see what is the velocity profile and we'll try to understand shear stress, what is the friction factors, all these things we'll try to understand. So is this clear to all of you till this point? Okay, सबको यहाँ तक clear? ये बहुत simply analysis है. Okay, so mathematically we know certain terms are zeros. So if you substitute zeros and थोड़ा simplify किया तो these definitions are the thing. This expressions is what you will get. Okay, now let us try to solve this equation. Now first of all, try to understand one thing. This equation is a second order differential equation in space. Okay, this is with respect to y. Okay, so y or x may be anything. So this is actually with respect to space and there is no involvement of time. Now if you want to solve this condition, if you want to solve this equation, this is second order in space. So definitely what should be your boundary conditions? How many boundary conditions you need? This is a second order in space. So you need two boundary conditions, right? So what are the two boundary conditions? First of all, let us write the equation. Equation is d square u by dy square is equal to minus, no, there is no minus sign I guess. Yeah, no minus sign. This is dp by dx, which is actually a constant. Okay, which is actually a constant. Now you have two boundary equations. What are they? Boundary conditions. What are the boundary conditions? At y is equal to minus h. What is the velocity? Can anyone tell me? At y is equal to minus h means at this bottom plate, the layer which is in contact with the bottom plate, what's going to be the velocity of that layer? Come on, quick. What should be the velocity of the bottom layer of fluid that's in contact with this plate? Because at y equal to minus h, the interface is actually there. So that interface will be in contact with both the plate and as well as the fluid. So that interface is at 0 velocity. Okay, so this is 0. Similarly, at y is equal to h. At y is equal to h, this upper plate is the point. So at y is equal to h, this velocity is also 0 again. Okay, look, it's like a combination of maths and also physics. Okay, so these boundary conditions and all will like from physical insight. Okay, physically because of no slip condition, yeah, correct, no slip. So because of the no slip condition, the relative velocity between the plate and the fluid layer has to be 0. So that's how we have zeros. Anyway, let us solve this quickly. So if you integrating, this is mu into du by dy is equal to dp by dx into y plus some constant c1, correct? Now again if you integrate, this gives you mu into, or if you differentiate, for example, if you divide mu completely, okay, now if you integrate once again, integrating again with respect to y only, okay, with respect to y. This is actually constant, okay, so you can treat this as constant. So u is equal to 1 by mu into dp by dx into y square by 2 plus c1 by mu y plus c2. This is what you have, okay. So this is the velocity profile. Now you have two arbitrary constants, so to calculate two arbitrary constants you have two profiles, okay. So two boundary conditions. Let us substitute. At y is equal to 0, first of all let us use boundary condition 1. Boundary condition 1, okay. So what does this tell you? At y is equal to 0, u is equal to, at y equal to minus h, right? At y equal to minus h, u is equal to 0. So if you put y equal to minus h here, 0 is equal to, okay, so 0 is equal to, when you put y equal to minus h, this is minus h square, no, this is plus h square actually, because minus h whole square is h square by 2 mu into dp by dx minus c1 h by mu plus c2, okay. Also if you apply the boundary condition 2, let us see quickly. At y is equal to h, again your u is equal to 0, so 0 is equal to h square by 2 mu dp by dx plus c1 h by mu plus c2. From these two equations you can understand something. Tell me what is that? From these two equations, look, this equation and this equation, they have only one term varying. So can anyone tell me something about these two equations? By looking at these two equations you can talk something about this constant c1 and c2. What is the value of c1? What is the value of c1? Come on, quick, you can do this. What is the value of c1 actually in this? You can easily understand, right? If you look, this is 0, this is 0, this term and this term are same, c2 and c2 is same. So you can understand one thing, that c1 is also 0, okay? Because if you do first equation minus second equation or second minus first, you can clearly understand c1 is equal to 0 in this case, right? Because see, if you subtract 0 minus 0, 0, these two terms gets cancelled, c2, c2 gets cancelled, 2 c1 times of h by mu is what you have, okay. H by mu is not 0 because h is some physical value, mu is also some physical value, so c1 has to be 0, that's it, okay. So if c1 is equal to 0, this implies c2 is equal to, if you put c1 equal to 0, c2 is equal to minus h square by 2 mu into dp by dx actually here, okay. So therefore your velocity profile is like u is equal to 1 by mu dp by dx y square by 2 plus c1 is 0 plus c2 minus h square by 2 mu into dp by dx actually here. So you can understand u, if you write this u, if you take h square by 2 mu constant, h square by 2 mu, this minus sign if you send inside, minus dp by dx, this expression is 1 minus y square by h square, that's it. So this is actually the velocity profile in this case, velocity profile, that's it. Is this clear to all of you till this point? This is the velocity profile at any point in this flow. Just it's a simple solving of one differential equation with boundary conditions, okay. From here to here there is nothing job of a fluid mechanics engineer, it's just a mathematical job, clear? Solving a differential equation with two boundary conditions, that's it. That to an ordinary differential equation. Understood? Yes or no? Please type in the chat box. Is this clear to all of you till this point? So we know that velocity is 0, w is 0, and you know u, we have got the understanding. At any point in the flow you can calculate what is u now, okay. And once you calculate u, you can calculate pressure gradient easily. Let us suppose that u is equal to, if you test u at different points, you can easily calculate what is the pressure gradient in the flow. These are simple understandings, okay. Now let's get back to the things, okay. Before going to boundaryless, we have some things to do. Now clearly this equation is not depending on any alpha or something, so this profile is parabolic because you can see a y square term, okay. So you can see, if for example if I sketch it, if I take any section of fluid particles here, and this is the midline, where the coordinate system is established. Okay, so let us define the coordinate system here. X, Y, and also Z. This is the coordinate system. Then at this point, here the velocity is 0, here the velocity is 0, clearly it increases, so it takes a parabolic shape. Okay, so this is actually a parabola. So you can see this is actually parabolic. This is for velocity profile. Velocity profile. Okay, now let us try to understand some things. Clearly this is 1 minus y square by h square. This is constant for a given system, for a given physical system. This h is fixed, this mu is also fixed, correct? Because let us suppose if you are flowing some oil, then oil has a fixed dynamic viscosity. This term is fixed. Now clearly if u has to be maximum, clearly this y has to be 0, yes or no? Because this is a subtraction and this term is always positive, and for this expression to be maximum, this expression should be maximum. For this expression should be maximum, this y square by h square should be minimum, okay? Because it's a subtraction. So for the minimum value of y is actually at 0. That means clearly also physically you can understand this is the point which is away from both the walls. So definitely the maximum velocity is along this center line, okay? So using all these understandings, these plates are fixed anyway. We are fixing these plates. So clearly this is u max. U max here. So let us see, u max is at y is equal to 0. So this implies u max is equal to h square by 2 mu into minus dou p by dou x or dp by dx. This was 1 year gate question actually. Okay, they've asked what is the maximum velocity in flow between two fixed plates actually. Okay, so h square by 2 mu, of course depending on the coordinate systems this constant can change here, but actually if you want to use 2, then you have to take the spacing h as half of the total distance between the two plates. Okay, because sometimes what people do is they, instead of assuming the coordinate system here, they start here and do the analysis, because of which this constants will change. Okay, but when if you want to apply this formula, you should take this value of h as half of the space between the two plates. Clear? So this is h, and it's always advantageous. Normally if you see, whenever flow is symmetric, it's always better to take the coordinate system at the plane of symmetry. Okay, so that your analysis mathematically solving gets easy. That's it. Okay, so anyway, this is what you have. Now shear stress. If you talk about shear stress, normally these clearances are small. So if you write tau w or tau is equal to mu into dou u by dou y, or since here u is only function of y, you can write as du by dy actually at any point. So tau is equal to mu into, what is du by dy? If you differentiate this with respect to y, this h square by 2 mu minus dp by dx is constant, correct? So h square by 2 mu minus dp by dx is actually constant. Okay, so you can pull it out. Derivative of this is minus 2y by h square, correct? So this is minus 2y by h square, because if you differentiate this with respect to y, you have minus 2y by h square. Now you can see this 2 and this 2 gets cancelled, mu gets cancelled, h square gets cancelled. So tau is equal to y times of or minus y times of or y times of, let us just a minute, this can be written as minus y times of minus dp by dx is what you have. Okay, so this is the case. So tau is equal to minus y into dp by dx. Now you know this minus dp by dx is constant. So if minus dp by dx is constant, tau is of the form some constant times y. So what is the variation? Linear, parabolic, cubic, something? What is the type of variation? Means if you take a shear stress at this point, so if you take a shear stress at this point, then can anyone tell me what is this variation? Linear variation, correct? So shear stress actually varies linearly. Linear variation. Okay, now clearly you can understand dp by dx is generally negative because of the pressure gradient, the flow is happening, and this negative of negative is positive, so this is minus y. So the meaning of that is the shear stress at this points is like this fashion in general. Okay, so it is of this fashion because the flow is happening in this particular direction. Okay, so this is actually a linear variation for shear stress. Shear stress actually. Now, I want to ask you one thing. What about the discharge actually that happens? Okay, so for discharge, what you can do? You can actually calculate the discharge to a small section. Let us suppose if this is small section dy, width of the plates, for example, 1 unit. If I take width of the plates is 1 unit, to this small section, the amount of flow that flows is u. If the velocity at this point is u into w into dy. For example, if I take this w as per unit width, this is what the small elemental discharge, correct? So if you want to calculate the total discharge, integrate this from minus h to plus h, because minus h is the lower limit and plus h is the upper limit in this case. Okay, so u into dy is what you have here. Now if this is u into dy, what is the expression for u? Minus h to h. U at any location is given by h square by 2 mu. This is 2 mu, right? H square by 2 mu. Okay, minus dp by dx into 1 minus y square by h square times dy is what we have. Okay, so simple integration, single variable integration you can do. So the discharge which flows through this between the fixed plates is like q is equal to h square by 2 mu into minus dp by dx. यहाँ तक सब कांस्टेंट्स है. Integration of 1 y within the limits minus h to h, so y minus integration of this term is y cube by 3h square within the limits minus h to h actually. Okay, so this expression you have to calculate from minus h to h. So if you substitute, let us check something. We'll get h square by 2 mu minus dp by dx into, now first of all if you put h here, h minus h by 3 is what you have, minus, if you put minus h, this is minus h plus h by 3, correct? This is what we'll have, because when you put minus, minus of h cube is plus h cube. So now you can see this is minus h by 3 and minus h by 3. So this is h minus of h minus h. So this h and this h gets cancelled. No, this is like plus. If you simplify this, let's check. Q is equal to h square by 2 mu into minus dp by dx into, so what is the flow rate actually? Discharge. So h minus of minus plus h, so 2h minus, this is minus h by 3 minus of plus minus, so minus 2h by 3, correct? So you can cancel these two all over. So q is equal to h cube by mu into minus dp by dx into, so if you take this h out, 1 minus 1 by 3 is actually 2 by 3, so 2h cube by 3 mu, that's it. Okay, so because this answer is 2 by 3, so the discharge flowing through the channel is 2h cube by 3 mu into minus dp by dx actually. Okay, so you might have seen this expression, right? Why I am calculating discharge? Because I want to calculate the average velocity. Okay, so what is the average velocity of the flow? So what is average velocity? You know, practically the velocity varies at any cross section as per parabolic variation. Okay, but let us suppose if you assume a constant velocity here. Okay, so let us suppose at every section you have certain constant velocity. Okay, so at every section you have some constant velocity, like in this case this is the constant velocity at every section, at every particle. Okay, so if this is the velocity which is uniform at every point, then the velocity which gives you the same amount of discharge is the average velocity. Okay, so this is u average. U average. Okay, now let us calculate what is that average velocity. So first of all, is this integration clear? I'm just doing bit of maths, that's it. Okay, that too simple maths, integrations, differentiations, that's it. Is this clear to all of you? Did you all get this expression? H cube by 2 mu into minus dp by dx, right? Yes or no? So please type in the chat box. I'm just doing integration, that's it. Okay, for flow through pipes I'll directly give the results. I won't do the detailed analysis. I don't show you the derivation, but this is a bit of important, so I'm showing. Okay, fine. Now if you see, so what is average velocity? Q is equal to u average into flow area. So discharge is 2h cube by 3 mu into minus dp by dx. is equal to U average. We don't know what is U average into flow area 2h into 1, correct? Because at any given point the area of cross section for the flow is, this is 2h multiplied by width actually, okay? So 2h multiplied by width is 1, so 2h into 1 is the flow area. So if you simplify this, you can see 2 this h cancel, this h square actually. You can understand one thing, U average is equal to 1 by 3 into h square by mu into minus dp by dx. You can adjust a 2 here, a 2 and a 2 here, okay? So can I write like this? Just to this term I have adjusted a 2, that's it, okay? All simply bringing this 2 here, that's it, okay? Now can anyone tell me what is this term? Have you seen this? What is h square by 2 mu into minus dp by dx? In your notebook it is there, please check, just one page ahead. What is this value? U max, correct? So that's nothing but your U maximum, yeah, here, okay? So you can see this is your U max, so therefore this is your U maximum. Therefore clearly you can understand one thing, U average is nothing but 2/3 times U maximum, okay? So this is what you have. This relation is a bit important again, because sometimes what they'll ask you to calculate what is the maximum velocity, what is the average velocity and all. If you don't know this relation, average is 2/3 of, in exam I see many students even in offline classes when I teach fluid mechanics, they are confused whether U max is here or U max is here. They'll confuse between this ratio. Please understand, average velocity will be always less than maximum velocity, okay? So definitely that's what maximum is, like it's the biggest, it's the top of all, okay? So definitely this will be some part of this, so you can adjust the fraction accordingly. Don't waste time in exam or in while solving question by looking at 2 by 3 or 3 by 2, all these things. Clear? I just want to go for one more detailing, one last detailing. You can understand something like, yeah, here shear stress at the wall, which is tau w magnitude, okay? So shear stress at maybe y is equal to minus h or y is equal to h. If you see, this value is nothing but, if you put y equal to minus h, for example, h into minus dp by dx, correct? So this is what we have, h into minus dp by dx. Now you can see one thing, we define something called skin coefficient friction or skin friction coefficient, skin friction coefficient, which is magnitude of wall shear stress by this kinetic head, half rho U average square actually, okay? So this is what you get, half rho U average square actually. Now what is this shear stress magnitude? H into minus dp by dx by half density into U average square. So U average square can be written as, so U average square is equal to 2/3 of U maximum, or let us write directly square of this 4 by 9 into square of this h power 4 by 4 mu square into minus dp by dx whole square actually, okay? So minus dp by dx whole square. So one term gets cancelled, okay? So this gets cancelled, h will also cancel one cube here, and still what you can do, this 4 and 4 gets cancelled. So you will end up with something like this 18 is in the denominator of denominator, so you can send it on to the top, 18 mu square by 18 mu square by we'll do one thing, instead of converting both, we'll take only one we'll keep it as U average itself, okay? Because I want to show you one important thing here. Out of this U square, we'll keep one mu average as it is. So tau is first of all h into minus dp by dx by half times density into, so U average, one expression for mu average is 2/3 h square by 2 mu into minus dp by dx into U average is what I'm keeping, okay? So try to understand, out of this square, one term I'm keeping as it is, one term I'm substituting for the expression of mu average, okay? Now you can understand this minus dp by dx minus this h and this h2 and this 2 gets cancelled. So if you try to understand things, we have 2 3s are 6 on the top, okay? So this is 6 and so 6 on the top, that's it, right? So 6 divided by, and this mu can also go to the top. Mu can go to the top. So we have rho u average into h actually here. Okay, so rho u average into h. If you see something here, you know Reynolds number is equal to rho u average into hydraulic diameter by mu, correct? Rho Vd by mu. Normally this d is actually the hydraulic diameter, okay, which we will okay, right now I'll tell you. dh, if you see carefully, dh is something called hydraulic diameter. So clearly this dh is like 4 times of cross sectional area of flow divided by wetted perimeter. Wetted perimeter. Okay, so this is wetted perimeter. Normally in case of pipes, what's happening is, see, if this is a pipe, for example, and this is a cross section, I mean it has a diameter d, and let us suppose the fluid is flowing completely. Then if you calculate hydraulic diameter, 4 times of area of cross section of the flow. Whenever, so is this lecture sufficient for ESC also? Except very few theoretical points like valves, okay, valves and all. Apart from that, it's 100% useful even for ESC mains, pakka. Okay, like very few points like that too in chapters like flow through pipes, there will be certain empirical relations. Okay, so apart from that, it's completely useful. Okay, anyway, so what we are doing, hydraulic diameter. Okay, so whenever this fluid is filling the complete pipe, you have pi by 4 d square divided by wetted perimeter. This word wetted is very important. Okay, wetted. So whenever fluid is flowing, what is the perimeter of the pipe the fluid is wetting? It is nothing but the circumference of this circle, correct? So pi d. So whenever you simplify, 4 pi d, and this d cancels, and that's how you get your hydraulic diameter as a d for pipes. That's why here in this hydraulic diameter you put d here. Okay, but let us suppose if they give you square pipe or rectangular pipe or maybe some channel like this, how do you do? Look, 4 into cross sectional area of the flow. Now this spacing is 2h, width of the plate is w, then clearly what happens, this cross sectional area of the flow is like cross sectional area of the flow is like 2h times 1, for example, by wetted perimeter. So wetted perimeter is like, see, this is the channel. If you take the side view, here we are leaving it. Okay, so I hope you can understand the things. See, practically on this side there is no boundary. Okay, so there is physically no boundary to wet. So this gap you can take as h plus h, which is 2h again here. Okay, so this hydraulic diameter is actually, if you have width here, this is 4 times of width is what you have the dimensions, and width if you take as 1, that value is 4 anyway. Okay, so you can understand one thing, this mu rho u average into h, you can convert this. If you write a 2 here and if you also write a 2 here, then 2 into 6, this gives you a constant which is actually your 12, and you can relate this quantity to somehow as your Reynolds number, and you can get CF is equal to 12 by Reynolds number, which you generally see. Okay, so there's a question, so wetted perimeter please explain kar dijiye. Yeah, when fluid is actually flowing, the complete length over which the fluid wets the complete surface, that's what. Okay, similarly here in case of channels, like for example if this is of height 2h, then the width of the plates, for example, okay, so this is w and this is also w in this case. Okay, that's it. So this w and this w is actually wetted by the fluid. Okay, so physically there is no, I think I have written 2, sorry, I made some mistake here, just a minute. What did we write here? Just a second. 4 into area of cross section of the flow, w into 2h divided by the fluid is wetting a 2w. So 2w gets cancelled, 4h. I think I have written w, right? No, that's not w, that's actually 4h. Clear? Okay, is this understandable to all of you? Whenever the flow is happening in the channel like this, whatever is the width of the plates, the flow actually wet this part, correct? Because physically there is no boundary present on the other sides. I think this is what you got confused, right? Yeah, because I made a mistake. This is actually 4 times of h. Okay, so if you make a 4 here, then what we have written, it should be 4, right? It is 24. Yeah, correct. This is 24, sorry, because it should be not 2, it is 4. If you want to adjust, because here it is not 2, it is 4 actually. So this is actually a Reynolds number, 1 by Reynolds number, of course, and this constant is 24. So you get 24 by Reynolds number. Yeah. Okay, I think that there you got confused because I missed that 2 in the calculation somewhere in this hydraulic diameter. So this is what you have. You might have seen this expression, correct? So why skin coefficient of friction is important is like skin friction coefficient in physics, in physical implementation, it talks about how strong is the shear at the wall. Okay, it's like the intensity, you can see. So therefore, how strong is the shear is what you have generally. Okay. So is this points clear to all of you? If these are clear, just I'll jump to flow through pipes. Okay. So is this clear to all of you or not? So please type everyone. Vanjit, Hrishikesh, Sky, Aryan, physics, daily dose. Okay. I hope it's clear. Next slide. Next slide, this one. Yeah, hydraulic dia. Okay, now let us quickly jump to flow through pipes, which is the Hagen-Poiseuille flow. Hagen-Poiseuille flow, which is flow through pipe. Okay, so I'll give you the expressions directly, okay, because you can do actually in polar coordinates in detailed course. Generally I do the derivation, but here the time is a bit short, so I'm not able to do that derivation. Just a minute. So this is tight, this is tight, then why this is not tight? Okay, let us say somewhere here. Okay, so this is the pipe. So let us suppose if you have the particles here again, which are moving in this direction. So normally, you know, this is the radial coordinate, then this is the theta coordinate, and this is z actually. Okay, so this is the z coordinate. So these are, we establish a coordinate system in cylindrical, r, theta and z. Now if you do the same analysis again, if you apply continuity, so normally in continuity in polar, if you see, we have continuity dou Vr by dou r plus Vr by r plus 1 by r dou V theta by dou theta plus dou Vz by dou z. Normally if you see in polar, you have the velocity profile as a radial component into Er cap plus azimuthal component into E theta cap plus Vz Ez cap actually here. Okay, so this is what we have. So this is continuity. So pipes are only cycle in a reason. Stresses, basically hoop stress is the reason. Okay, we'll see that maybe in right now I may not explain you, but normally you can ask your machine design, or yeah, in strength of materials also you can ask. I think hoops are better. Okay, normally if you do the stress analysis, you know the hoop stress, right? Normally in case of pipes, or normally for any cross section, if you take a random cross section like this, the stress management, hoop stress management is better for circular. You can see this derivation using this equation. This is of course for bending. You can see whenever certain pressure is exerted like this in all the cases, and if you apply certain values of the A, you will find out circular cross section is the optimum cross section in that case. Okay, now let us see. So this is for continuity, and clearly here in this case this Vr is 0 and V theta is also 0. This is basically from axisymmetry, and this is due to physical boundary. Why I'm talking this is, look here, let us suppose if there is a particle here, this particle, if it starts moving in radial direction, very soon it will get in contact with the boundary wall, means basically the pipe wall, and this VR gets arrested. Yes or no? This VR cannot sustain for a long time, even though because of few local disturbances, even if there is some radial component of velocity, means if this particle, which is somewhere here, is trying to move in the radial direction, very soon it will get in contact with the pipe wall, and physically the radial component of velocity gets nullified very soon. Okay, and also we are assuming the particle is not actually doing any rotation about axis, it is just moving linearly in the z direction. Is this clear to all of you? Okay, so please type in the chat box, is this clear to all of you till this point? Are you all clear with the assumptions that we are doing? Like, see, what we are doing is actually this particle, if it tries to move, to deviate from this motion, and if it tries to achieve this motion, which is nothing but in the side view, the particle is moving radially, very soon it will get in contact with the pipe wall, and within a very short time, the radial component of velocity gets 0, okay, because the particle cannot move further, okay, so it gets restricted. Similarly, we are also assuming the particle will not actually rotate about this axis, means in the side view, if you see, this particle will only travel in the z direction straightly, but it won't rotate about the axis of the pipe. Okay, so these are the assumptions. So therefore, these two are zeros. So you have only Vz, which is only the flow velocity in this direction. Okay, and if you apply the Navier-Stokes or momentum equation, which is basically the Navier-Stokes equation in this case, momentum equation in radial direction and theta direction. So radial, if you see, do you want to see the equation? Have anyone seen the Navier-Stokes equation in the polar coordinates? Only due to pressure gradient in z direction, in nullify in radial direction. Yes, because the pressure will try to push the flow only in the forward direction, right? That's why. Did anyone of you see Navier-Stokes in polar coordinates anytime? No? You want to see? You want to see? Yeah. No is why you don't want to see, or you have never seen? Okay, I'll write only for the radial component. Okay, for theta it's similar. Clear? Yeah, for radial component I'll write. Okay, so that you can understand. So neglecting body force, anyhow gravity is not in the picture. So minus dou p by dou r plus mu into del square VR. Okay, so what is this del square VR in the radial component? Okay, so let us see, dou square VR by dou r square plus 1 by r dou VR by dou r minus VR by r. Okay, so till this point it's clear. Then after this is minus VR by VR square. Okay, so this is VR square by r, and then after plus 1 by r square dou square VR by dou theta square plus, no, this is minus then, so minus 2 by r square v theta by r. Okay, so this is like 2 by r square v theta by r plus dou square v radial by dou z square is what you get. Yeah, correct. This is the expression, is equal to density times dVr by dt. For again, you know the expansion, like this dVr by dt is like, total you have 6 terms in this, 1 2 3 4 5 6. Yeah, this is like dou Vr by dou t plus Vr into dou Vr by dou r minus, no, this is plus v theta by radial dou v theta by dou, no, this is dou Vr by dou theta plus dou Vz, no, this is dou Vr by dou z, like that, this plus or minus v theta square by r. This is what you have. Clear? So this is the Navier-Stokes equation. You have seen it in the NASA document of fluid mechanics, this one, right? Is this equation important for GATE? Not at all. Okay, just I'm showing you why this, how this comes. Okay, so this is for radial. So similarly you have theta with bit of variations, here will have plus and here will have some other change, and then for z direction. Okay, but anyway, right now we are not doing the things. I've just written once to show you that this is the radial component. Okay, similarly you'll have for the theta and also the z components. But anyhow, I know you guys will be panicked by seeing this equation, so sir थोड़ा time और ध्यान लग के कुछ समझ में, बड़ी बड़ी इक्वेशंस ले देते दिमाग फट जाएगा हमारा. ठीक है, You need not write this equation as of now. Even even I don't remember this in a very first go. Like when I was studying fluid mechanics in my BTech, I remember this equation. But generally, as you keep on using, because I keep on dealing with this flow through pipes many times. When I was in HPCL also, we are talking about the pipelines and all lot of stuff we are talking. So anyway, right now we are not focused much on this, but anyway, we'll see the final result. Okay, the main important thing that we need is what is the velocity profile, correct? That's what we have to understand. Clear? Okay, fine. Okay, velocity direction और वेक्टर v बारे में बहुत कंफ्यूजन होता है. सॉरी, वेलोसिटी डायरेक्शन और वेलोसिटी v. Look, vector is always accompanied by direction. Okay, so first thing is, look, whenever if I write vector, this has a particular direction. In this case, because of these two components becoming 0, this v has the direction of this z, which is nothing but the flow direction. That's it. Okay, and this vz is component, and this is the total velocity vector. Clear? Okay. I want to talk something about vectors. Actually, recently, I had a chance to meet Professor 𝐂𝐤𝐧𝐤𝐬 sir. You know 𝐂𝐤𝐳 sir, right? Concepts of Physics. How many of you have used his book? I think almost everybody when you're preparing for your JEE or mains or advanced. Correct? You all know, right? 𝐂𝐤𝐳𝐤𝐬 sir. You know him? Correct? So recently I got a chance to meet him. Yeah, intermediate also you might have used. So recently I've attended one of his talks actually, and I got a chance to meet him luckily. So regarding these vectors, he was talking about very interestingly. Okay, like he was telling, sir, main bus nikal diya. Fine, it's okay, cool. So he was telling that if you take a boy, like for example, let us take a 2-3 years boy or girl, a child basically. So this child knows very well about vectors. He knows very well about velocity. He knows very well about force and all. And he told an example actually about this. Like let us suppose you are standing, and if there's a small child, okay, if you give him a ball and if you ask him to throw towards you, okay, let us suppose you tell him that we'll play catches and you throw the ball to me, then he knows that if you are far away, he knows that he wants to throw the ball very fast or very as much as possible, and if you stand very close to him, he throws the ball slowly. Correct? Which means he knows that your force for having for traveling long distance, the initial velocity what you should give to the ball should be high. So that means the force what you should give or what you should use to throw the ball should be high. That means he clearly know F is actually equal to m dv by dt. For having large distance traveling, this dv should be large. So for this dv, F also should be large. Correct? So this boy knows this. Maybe not in a mathematical form, but physically he knows that if the ball has to travel long, I have to throw it heavily. Okay, means the force what I have to apply should be large. Correct? Similarly, he also know one more thing. This also he know. How come? Let us suppose if you are standing here, he throws the ball only in your direction, right? If you stand here, he won't throw the ball in the different direction. He throws exactly at you. Means he know if the ball has to travel in this direction, the velocity of the ball has to be in this direction. So the force applied has to be in this direction. Okay, so that's what he know. Clear? So the main thing is schools, like the statement what he quoted was this, even we felt very fact. Normally when you don't go to school, you keep on learning at every time. Okay, it's not like 10 a.m., 11 a.m. or 12 a.m. or something. You actually keep learning the things. Or sorry, 12 p.m. You will keep on learning the things. But once you go to school, ये लोग क्या बोलते हैं आपको? बेटा 8 बजे से 9 बजे तक सिर्फ सोशल स्टडीज पढ़ने का शुभ मुहूर्त है. ओके, सो उस टाइम पे इंग्लिश मत पढ़ना, साइंस मत सीखना, मैथ्स मत सीखना, सिर्फ और सिर्फ सोशल स्टडीज पढ़ने का शुभ मुहूर्त है. करेक्ट? सो दे विल एक्चुअली कन्फाइन यू, राइट? सो दिस इज व्हाट जनरली इट हैपेंस. So if some of you become teachers, if some of your students are studying say some other thing in your class, don't get angry or anything. Okay, this is what he told. A great legend again. So recently he was a national awardee, you know this. Okay, so sometimes when you get chance to meet people like this, you definitely make use of them. Clear? Fine. Okay. So anyway, since you asked about vectors, I'm just telling about that. Okay. Simple things. So fine. Anyway, you need not remember this equation. I'll write a hint here. Otherwise, someone who see it later, they'll feel that I'm teaching all this. Need not remember. At least forget. Okay. And also for ESC, I think for ESC, some questions they may ask you if you need. But anyway, now the main job is what is the profile. So after doing bit of algebra, solving differential equations and all, you will get this as r square by 4 mu into minus dp by dz, which is the pressure gradient, 1 minus r square by r square. So what is small r and capital R? This is the capital R, you know, this is the radius. This is radius is equal to 0, center line, and small r is equal to small r at any radial location. Okay, so this is small r, for example. Clear? So can you please explain that component written in front of the radial every time? I just have memorized this. Where? Can you please explain the component written in front of the radial? What is this here? Somewhere here. Where? This derivatives is what you're talking. I mean, this dou square by dou r square 1 by r. Is that the terms you're talking? Above that one, this one. Explain that component written. Acha, this one, Laplacian. This one is what you're talking. This one, right? Del square. Correct? Is that what you want? Yeah. This is actually Laplacian operator. Look, if you want to talk a bit, this is Laplacian operator, because basically this is from the Laplacian equation, actually Laplacian operator, and this del square is actually obtained by del dotted with del. I'll explain in Cartesian, you may feel little easy. In Cartesian, you know, del is actually dou by dou x. You know practical meaning of this del, right? In maths and all we will see. Whenever you see del actually, so del gives you, let us suppose it normally apply this del on a scalar or a vectors also sometimes. So when you apply on a scalar, like let us see the simple cases. If you take a scalar function, let us suppose if temperature is there, for example, okay. So in this room, let us suppose if I take a plane, okay, 2 dimensions I'll take simply. Let us suppose if I take a horizontal plane, okay. So in this horizontal plane, temperature can be different at different positions. Okay, let me take an example and let me talk about this. So if you take a 2D plane, for example, okay, and at any point here, there is temperature. So this T is signified by X and Y coordinates. Let us suppose in 2-dimensional space. Now what this del physically tell you is, if you apply del of T, gradient of temperature, you will actually get some vector. Okay, so something into I cap, so Txi plus T, or if you see in general, you know, in Cartesian this is like dou T by dou Xi plus dou T by dou Y j actually here. Okay, now sorry, there's a big comment. Okay, can I edit this comment after this? Okay, because it's a very long comment. Fine. So dou T by dou Xi plus dou T by dou Yj. Okay, now practically what is del? You know, gradient. This is normally called gradient. Gradient. Okay, so whenever you say gradient, that means change. Like you say pressure gradient, okay, temperature gradient. So whenever you take gradient, the change in temperature with respect to certain change in distance is what you generally refer as gradient. Okay, now when T is depending on X and Y, it's not possible for you to calculate the gradient at an instant. Like for example, if you want to calculate gradient at a time, since T is changing in 2 directions X and Y, it depends at which particular point you are calculating the change. And also this term tells you partially, if you change your X by some amount, what is the change in X, and if you change Y by some amount, what is the change. So the vector sum of these two is nothing but this component. Okay, so this is like when you move your distance from this point by a small amount del x, what is the change in temperature. So that's given by dou T by dou X I bar, and this component talks about dou T by dou Y in the j direction, and the resultant of these two is this, which is actually the vector sum of those two components. So whenever things change with respect to multiple let us suppose if you have any physical quantity like temperature, pressure, or density, something, when they are changing with respect to multiple dimensions, it's not possible for you to consider all the changes in a single go. So what we do, we'll calculate the changes in the individual directions. Means in actual case, we'll calculate the effect of every parameter on this. Like for example, let us suppose if I say P is equal to what? If I want to calculate gradient of pressure, I can do the differentiation in terms of characteristic gas constant, temperature, and all the stuff. So when I do, we'll actually take the change of this T with respect to one parameter. So like this, we'll calculate due to all the parameters, and we'll do a vector summation, which is actually the gradient. Like for example, you see your Fourier law of conduction, they'll tell you Q is proportional to temperature gradient, right? This is actually a Fourier's law of conduction. Similarly here, whenever temperature is spatial in 3 dimensions, if you do, you might have derived the Cartesian equations and all. So you might have seen this equation, right? All of you might have seen this definitely. For isotopic, homogeneous, all these assumptions, del square T plus Q dot generation by K is equal to 1 by alpha dou T by dou T. Have you all seen this equation? So in Cartesian, in 3D, this is nothing but dou square T by dou X square plus dou square T by dou Y square plus dou square T by dou Z square. All this stuff you'll calculate. Again, this can also be calculated. This equation can be calculated using Reynolds transport theorem, because transport phenomena can be used for any transport of any fluid in any property, like it can be flow, fluid, it can be heat, anything. So this can be done. This equation can be derived in 2 steps using Reynolds transport theorem. If you take your capital B as energy, so small b is nothing but total energy per unit mass, which is internal energy. Okay, so if you do, you can actually calculate this. For solids, change in internal energy is nothing but mc dt. So if you substitute here, this k by OC alpha is what we get here on the right hand side, and this term will be actually from, if you divide this with time. All these things you can easily do from the Reynolds transport theorem very simply, like 2-3 steps maximum. Okay, even if you know the Gauss divergence theorem, still you can do this very easily. And del square using polar, we'll apply what are the radial, theta, and z directions, normally in case of nuclear rods and all. Okay, when I was in BRC, Bhabha Atomic, previous to PW, I was in BRC, Bhabha Atomic Research Center. So there, normally when you're doing the nuclear fuel packing, normally in the control rods analysis or in the heat analysis of the reactors, these equations, these heat transfer equations are very much, predominant. Okay, so anyway, we'll find some time for discussing all these things. Why this? Yeah, Laplacian. I hope I have answered your question. Who asked me this? Vivek. Yeah, Vivek. Did your doubt get cleared? This is del dotted with del again. Okay. Fine. Okay. So anyway, this is the velocity profile for any flow through pipe. Now, if you take a pipe, again, pipeline. Let me draw a short pipeline so that I can adjust the scale. Okay. Now, if this is a pipeline actually in which the flow is happening, then clearly this is parabolic equation. Again, you can see there is r square. So this guy is parabolic. Oh, sorry. Parabolic. So if you take something like this, at this location, the profile is parabolic. Okay. So at any section in a fully developed flow, okay, this is fully developed flow. So this is parabolic velocity profile. And if you talk about shear stress, because velocity profile is the main thing, so once you get velocity, you can calculate shear stress, whatever the things you want. So shear stress variation now. Shear stress variation, again, tau is equal to mu into minus dvz by dr. Many of you may feel normally we used to write only du by dy, okay, but here why this excess minus sign is coming? The reason for this is when you are writing du by dy, you can understand as y is basically the normal distance from your fixed plate, okay, or basically from your solid boundary. So from solid boundary, if y is increasing, then definitely your velocity also increases. But here you can understand radius is measured in a different sense. Radius is measured towards the solid boundary. Understood? Whenever you are writing du by dy, your y is measured away from the solid boundary, but here your radius is measured towards the solid boundary. So if you are going towards the solid boundary, definitely velocity decreases. So as vz increases, this radius should decrease, okay, right? Or as radius increases, vz should decrease. That's why there is a minus sign, like minus of temperature gradient in Fourier law. Clear? Now if you do this, let us see, you'll expect a linear variation. Tau is equal to mu into minus, if you differentiate this with respect to small r, we have r square by 4 mu minus dp by dz. So इस equation में यहाँ तक constants है, so dp by dz into, so in differentiation of this minus 2 small r by capital R square, then you can sense this minus and minus gets cancelled, r square, and what else we can do? This 2 can cancel this 2 here, mu gets cancelled. So we have tau is equal to, this is looking like z, sorry. So tau is equal to minus small r by 2 into minus, oh sorry, minus got eliminated now, no more minus outside, there is only inside, r by 2 into minus dp by dz is what you have as the shear stress, and this is also changing with respect to radius, and clearly this is a linear variation because you have only one r, okay. So this is a linear variation. Linear variation, clear? Now if this is linear variation, so at any section like this, you can see this is constant. So as radius increases, this tau should increase, and clearly the maximum shear stress is at the wall, undoubtedly, you know this, right? So this maximum shear, because as you move forward, the shear stress will decrease because velocity gradients will decrease, okay. So this is linear shear stress profile, shear stress, okay, shear stress. Now I want to tell you one thing, Q average or Q, if you do discharge Q is equal to, so how do we calculate? So let's see, if you take a small cross section and if you do the analysis, like for example here, in this case, if you take a small cross section, okay, so yeah, this is at some radial location r, and this thickness is a dr, for example, okay, that small strip thickness. So this is the elemental flow area if I am taking, then the flow through that elemental area is nothing but Vz into 2 pi small r dr, correct? Yes or no? This is the flow area. Can you appreciate? Because if flow is happening in this direction, and if you want to analyze at a particular cross section what is the flow, at this cross section take some small elemental area and you can integrate. Since we are doing in polar, it's advantageous to take a circular element which could easy the analysis, okay. Now you have to integrate this guy from 0 to capital R, that's it, because radius is equal to 0 and at the top notch point radius is capital R. So if you do this integration, you will get the answer. So what is Vz? Q is equal to 2 pi into R square by 4 mu into minus dp by dz, so these are constants, into integral r equal to 0 to capital R small r times 1 minus r square by capital R square dr, actually that's it. Actually when you write Vz, this term should be inside, but anyway that's a constant, so I have taken it out, that's it. Clear? Is this clear to all of you? Till this point is it clear? It's a single variable integration, you can simply do that, okay. So is this clear to all of you? Yes or no? Clear? Fine, okay. So if that's the case, then you can maybe do this. So Q is equal to pi r square by 2 mu minus dp by dz. So if you integrate this guy, let us see what you get. R into 1 smaller, so integration 0 to r, this is capital R, minus r cube, so integration of r cube is r power 4. So just a minute, because if these two terms has to be done, this is smaller, so integration is r square by 2, okay, minus r cube, so integration is r power 4 by 4, so this is r square by 4 again if you simplify. So this is r square by 4 is what you have. So q is equal to discharge. Anyway, if you calculate discharge to a pipe, discharge to a pipe is equal to pi r square by 2 mu, r square by 2 mu into this is r square by 4, half minus 1 by 4, so minus dp by dz, r square by 4 actually. Okay, so this is what you have. If you slightly adjust the terms, let us see, q is equal to pi r square, okay, into 1 by 2 times of r square by 4 mu into minus dp by dz is what I can write. Correct? So this is what I can write. Yes or no? This is the same expression. This expression is same as this. This pi r square I have pulled out. This 1 by 2 I have written separately. 4 and this mu I have written as 4 mu r square minus dp by dz. Now you can understand one thing. Clearly at this profile, velocity is maximum at r is equal to 0, center line. Okay. In this, if you put r is equal to 0, the maximum velocity is nothing but this term. Correct? So capital R square by 4 mu into minus dp by dz. So Vz max r square by 4 mu into minus dp by dz is what you have. Clear? Now if this is minus dp by dz, then this term which is here is nothing but Vz max. Okay, so this is flow area because pi r square is the flow area. So which means you can say q is equal to, if you take this as flow area, this complete term should be average velocity. So therefore you can say u average or Vz average should be equal to Vz max by 2. That's it. Okay, so therefore in case of pipes, average velocity is half of the maximum velocity. This is also gate question. There are many questions on this. Okay, you know, in case of flow through pipes, clearly average velocity is half of the maximum velocity, which you can understand from the simple analysis of discharge. Clear? Yes or no? So please type in the chat box. Is this clear to all of you? Everyone should type. Yeah? Clear, right? Till this point. So what we can do after this? So discharge is done. Fine. We'll do one thing. We'll calculate what is skin friction coefficient and friction factors. We'll get certain things. So first of all, let us see certain things that okay. So let us suppose there is a length of first let us calculate wall shear stress. Tau W wall is at radius is equal to capital R. Tau wall is nothing but tau at a radius is equal to capital R. Correct? So what is tau? This guy. So small r by 2 into minus dp by dz at radius is equal to capital R. So therefore wall shear stress is equal to capital R by 2 times minus dp by dz. Okay, so this is what you get. So this is the wall shear stress. Now why I am very much interested in wall shear stress is, if you calculate skin friction coefficient, which is again the measure of how effective is the viscous stress. So skin friction coefficient here skin friction coefficient here in this case is CF, is again magnitude of wall shear stress by half rho u average square, which you know, so which is Vz average here. Look, let me make you understand certain things. Tau W, this term, capital R by 2 into minus dp by dz. Okay, so divided by, now half into density into, let's do the same thing. 1 V average I'll keep as it is, 1 V average I'll substitute with it with this expression. Okay, so this is V max by 2 gives you V average, correct? So for 1 V average I'm writing half into R square by 4 mu into minus dp by dz. So this is expression for 1 V average, and another V average I'm writing as it is. Okay, means basically there is a square here. So out of that square, one I'm keeping as it is, one I'm converting in terms of the system parameters. Okay, now if you do this, you can understand this minus dp by dz, this gets cancelled. Then after one radius and this radius gets cancelled. Then 2 and this 2 will get cancelled here. Then you can see CF, skin friction coefficient CF, which is equal to, so what are the terms you have here? Let us check. This 2 and 4, if you send to the top, 8 divided by, okay, this 2 and 4 you are sending to the top. Then we have rho, I'll write maybe in the next here so that you can see the complete board. CF is equal to, skin friction coefficient is equal to 2 and 4 if you send to the top, 8 divided by rho VZ average velocity into radius by mu. This is what you have, correct? Yes or no? So type in the chat box, is that the expression you have? Because this 2 and 4 go to the top. So if 2 and 4 go to the top, then definitely rho R VZ average is what you have, divided by mu. Okay? Correct? Yes or no? So please type in the chat box. Clear? Now let us see something. If you multiply a 2 here and also a 2 here, this 2r is nothing but diameter, correct? So 2 8s are 16, 16 by rho average velocity into d by mu. Because for pipe, you know, this is diameter, so this is 16 by Reynolds number. That's why in all your problems, friction coefficient is 16 by Reynolds number because of this. Okay, so CF, which you generally call F dash, I think different notations are there for different books. So 16 by Reynolds number is what you have. Okay, so that's actually a skin friction coefficient, or generally you call it friction coefficient. Okay, clear? Yes or no? Okay, now let's understand one thing. Oh, sorry, just a minute, but why this happened? We have already changed the format now. Fine, right? But why? Guys, I think just a minute, something is going wrong here. Right? Till now it was blackboard, na? Why it turned green suddenly? We'll do one thing. We'll copy this, then we will erase everything and we'll use this as a blackboard. We'll keep multiple copies of this. Fine. Okay, now we'll copy the screens we need. Okay, for 2 3 more. Good. Now, okay, so this is skin friction coefficient. Let us talk about pressure drop in a pipeline. Okay, so which is very important concept in all oil industries. Pressure drop in a pipe. Okay, now let's see. You know, VZ average means the average velocity is equal to R square by 8 mu. Okay, R square by 8 mu into minus dP by dz. Correct? This is what you have, minus dP by dz. Now you can see, you can write this expression as dP is equal to minus 8 mu. What is not responding or what? Just a minute. Okay, fine. Anyway, so minus 8 mu by R square into VZ average into dz. Correct? We can write this. Now let us suppose you have a pipeline, for example. You have a pipeline here. So when you have a pipeline like this, so let us say this is Z1 because Z is this coordinate. So let us say this is Z1 and this is Z2, for example. Z equal to Z2. Z coordinate is in this direction, this is z. So let us say the separation between these two, z2 minus z1, is length. Okay, so in a given length, what is the pressure drop actually? So here it is P1 and here it is P2, for example. So let us see what is the difference between those two. So if you integrate this expression, at z is equal to z1, pressure is P1. At z is equal to z2, pressure is P2. So if you simplify this, P2 minus P1, because integration of dP is P, P2 minus P1 is minus 8 mu by r square into Vz average into L is what you have. Okay, so because z2 minus z1 is actually L, mu is constant, r square is constant, Vz average into L is also constant. So the pressure difference, or P1 minus P2, if you want to eliminate this minus sign, you can say P1 minus P2 is equal to 8 mu Vz average into L by r square. Okay, now you can do one thing, you can, because you know normally pipe is mentioned in terms of diameters. So if this is your pipe diameter, then clearly you can multiply a 4 here and you can multiply a 4 here. This 4r square can be written as 2r whole square, which is diameter square. So this gives you your P1 minus P2 at this point is 32 mu V L. I'm simply writing V average. I hope you can understand. This is actually your Vz average. Okay, but I'm writing V average, but I hope you can understand these two are same. Okay, V average into L by d square. Now generally pressure is measured in terms of head difference, head loss, because if you apply the energy equation, Bernoulli's equation and all, they are per unit head. Okay, so they are in terms of head per unit weight. So if you divide with Rg on all sides, then the head loss in pressure is like 32 mu V average L by rho G d square is what we have here. Okay, so this is what we have, and you can understand one more thing here. Normally, instead of calculating velocity, normally if you go for applications, main thing that focuses what is the discharge between 2 points. Okay, means what is the volume of fluid I should send in this pipeline. Okay, so for a given amount of volume, you can decide the pipe diameter and velocities. So instead of writing velocity here, because velocity changes with respect to pipe diameter, it's always suggestible to write discharges for calculating loss. No one will ask you, if you send the fluid at 10 meters per second velocity, what is the loss? People will ask you, if I want to transfer, for example, some 5,000 liters of petrol from Vizag to Secunderabad or some other place, let us say, to a pipeline, then for transporting this much amount of fluid, what will be the loss for a given diameter of the pipe? And they'll tell you the pipe diameter. So this is my diameter, this is my length of the pipeline. Length will be obviously the distance between the 2 points, and diameter, if they give you diameter, they'll ask you for this much amount of discharge, what will be the loss actually. Okay, so it's always suggestible to write this average velocity in terms of diameter, so I mean discharge. So we know V average is equal to Q by pi by 4 d square, that I can write as 4Q by pi d square. If you substitute here, HL is equal to 32 mu V average 4 into Q into L by rho G d square. So this can be written as 32 into 4, 128 mu QL by rho G d square. And this expression you might have seen many times. This expression is nothing but your Darcy-Weisbach formula. You might have seen this. Sorry if I write the spelling wrong, but Weisbach formula for calculating head loss in any pipeline. No, gravity you cannot neglect, because this gravity comes from the specific weight of the fluid, not from the fluid kinematics. Okay, did you understand this? This gravitational term comes from the property, specific weight of the fluid, but not from the kinematics of the flow. Clear? So you cannot neglect that. If you neglect that, there is no loss. No need of any pump and all. Okay, just you put some fluid in pipeline, it goes. No need of any pipeline. Pi term misses. Pi is also there. Where should be pi? Pi should be there now here. Correct. Pi d power 4, I guess, right? This is d power 4. D power 4. Okay. Yeah, pi d power 4, because this d square is there, in excess one more d square is there, so pi rho g d power 4. Correct. Yeah, now it's fine. V average expression बता दीजिए sir. Clear. Discharge is equal to flow area, which is cross section of the pipe, into average velocity. That's it. Oh, so V average is equal to 4q by pi d square. That's it. Okay. Fine. Okay. Now, is this clear to all of you? You might have seen all these formulas, very long. This formula actually gives you one concept of equivalent pipe diameter. We'll see what is equivalent pipe and all. But before that, I want to tell you one more thing. In this head loss, if you want to non-dimensionalize this term, okay? So head loss is equal, right? Again. Fine. Okay, so see here. This is head loss. You know, head loss is equal to 32 mu V average L by d square. Okay, so this is what we have, 32 mu V average L by rho g d square. Rho g is also there. Okay, rho g d square. Then if you try to sort of non-dimensionalize this, because you can see we still haven't reached the dimensional analysis, but if you see dimensional analysis, having certain non-dimensional combinations is very important. Okay, we'll see why it's important and all. But right now, if you try to, try to kind of formulate this, you can understand H is equal to, if you multiply it 2 actually, okay, so rho g d square into 2, and this is converts to 64 then, because 2 will give you 64 mu V average into L. So we'll do one thing, we'll multiply a V average and also a square here. Okay, so if you do this, then we have 64 into this term. If you write some sort of things here, mu divided by rho V average into d, so one non-dimensional term is here, into V average square is here, into, so V average square is here, into L divided by d. This is again non-dimensional, correct? So L by d, one we have adjusted, rho into g, into 1 by g is also there. Okay, so V square by g, V square by g. Okay, so V square by g, V average square by g is what we can have. Okay, so V average square by g, this is again having the dimensions of length, because this is non-dimensional, this is non-dimensional, so this should have the dimensions of head, because it is head actually. Okay, so this is what you get if you slightly do a bit of non-dimensional. Hi Dharmendra. So if you solve this here, HL is equal to 64, then clearly this combination, from your knowledge, this is Reynolds number with a denominator, into L by d into V average square by g actually here. Why this formula I have adjusted intentionally is, if time permits, could you give physical intuition of body force and forces in surfaces and how they are considered and neglected? Okay, I'll talk after this. Okay, so see here, why I have done this non-dimensionalization is, once you go to dimensional analysis, you will come to know, if you try to model anything, let us suppose if I want to generate a pipeline, let us suppose for a length of 1000 kilometers. Okay, in lab, before going for the field, actually before installing the pipeline and all, you have to do certain testing. Okay, so when you are doing testing, it's not possible for you to generate a pipeline of 1000 kilometers in your lab. Okay, so what we do, we'll apply something called dimensional similarity, which we'll see in dimensional analysis. So if you do this dimensional analysis, having certain non-dimensional combinations between the prototype and the model is important. Okay, there should be certain similarity between the non-dimensional terms. So if you try to bit of sort non-dimensionalize this is a non-dimensional term because L by D, length by length scale, so there is no dimension. This is also no dimension. You can understand one thing, this HL is actually proportional to your average velocity square. This is one very important understanding here. This is one very important understanding. I think 2 is also there here, V square by 2g. Yeah, kinetic head is V square by 2g. So 2 is also there. So V square by 2g. So anyway, you can understand this HL is actually proportional to the velocity square. So if you try to move the fluid at higher velocities, definitely the losses involved will be definitely high. LHS is equal to RHS in terms of dimension. Yeah, in terms of dimension they are equal, right? This is kinetic head, you know, right? Kinetic head in Bernoulli's equation. So this is kinetic head, this is HL. Now one thing that you know is this F, this is normally denoted with F, and this is like some factor which you call friction factor. Friction factor. Now why people are interested in this friction factor is, you might have got it out, why this multiplication of 2 I have done intentionally. Okay, even if I don't multiply 2, 32 is still a good constant, but why I am doing, whenever people, before going for inviscid flows, when people are analyzing when people are analyzing inviscid flows, actually in Bernoulli's equation you can actually measure pressure at any 2 points. Also you can measure the kinetic head. So they somehow brought to know that this head loss can be related to the kinetic head in the flow. You know, this is called the kinetic head. In Bernoulli's equation, if you write P by OZ plus V square by 2Z, we have seen, correct? So plus Z is equal to some constant, all this stuff. So here you can see this V square by 2Z is actually kinetic head. So they want to relate the head loss in terms of kinetic head under certain non-dimensional cases. Okay, so that non-dimensionalization in terms of kinetic head will actually give you a 2 here, and that's why this 64 is actually the 64 by Reynolds number is actually a factor which you should multiply this. Okay, because this ratio will be same L by D for when you design a pipe. So this friction factor is what you have in terms of this friction factor comes when you express head loss in terms of kinetic head of the flow. Clear to all of you? Kinetic head, and this F is actually 4 times of CF, because you know CF is 16 by Reynolds number, we have seen somewhere. So F is actually 4 into CF. So sometimes people denote this as F dash, capital F in some books. Okay, and this analysis was actually done by Moody. Okay, you know Moody's chart, correct? Normally later when you go for fictional turbulent flows, you can see Moody's chart. In this Moody's chart, this 64 by Reynolds number is what we can get for the laminar flow. Moody's chart is between the friction factor and the roughness of the pipes and various other parameters. So L by D ratios is what you will have in the Moody's chart. So when you do this analysis, you will find out this F friction factor is 4 times of CF. Okay, are you all understanding this concept? Why 32 is coming, why 64, why 128? All these multiples of 4 they comes in adjusting the diameters, converting to certain non-dimensionalization. Okay, because many times I see people mug up and they are very much confused about these 2 things. Especially they'll write 16 by Reynolds number, sometimes 16, 64 sometimes. You know, this all confusion should be avoided. Okay, clear to all of you, everyone? Now one important point here I just want to mention. So this 128 dash switchback I have shown you, and this friction factor anyhow. Okay, and I want to show you one more thing. Actually there is one important thing which is called, because since we talked about Bernoulli's equation just now it came in my mind, there is something called kinetic energy correction factor and momentum correction factors. Normally this is denoted with alpha, and also momentum correction factors, which is beta. We are doing for laminar flow first of all. So the name itself tells you have to do some correction to the kinetic energy and also to the momentum. Let me ask you one thing. When you are applying Bernoulli's equation, P1 by OZ plus V1 square by 2Z plus Z1. Let us suppose if there is a pipeline, for example, at a point you are applying this. Okay, when you apply is equal to something P2 by OG plus something. If you do up this, when you are substituting this V1 at this section, clearly you know every fluid has certain viscosity. But when you are applying this Bernoulli's equation, the main assumption is actually the fluid is inviscid and the cross section is same. Okay, but later at this point you recognize there is viscosity in the fluid, and the viscosity will not allow all the layers of the fluid to move with constant velocity. Okay, so that means in this expression in which you are neglected the viscous effects, you have to change this V1. Yes or no? Clear? This V1 what you are substituting, which you are assuming to be uniform at every point in this section, is not a very considerable assumption there. Okay, so therefore what we can understand is this V1 or this kinetic head weather requires some correction. Okay, you have to multiply some, as you know, these are factors, so you have to multiply certain factors to make this expression suitable for the actual flow conditions. Okay, and in actual case what you write is, you write alpha 1 P2 by OZ plus alpha 2 V2 square by 2Z plus Z2 and all. This is how you actually write the Bernoulli's equation in actual cases. In exam, if they don't mention kinetic factors, you just go with the equation what you know. If they mention kinetic energy correction factors, these are the places where you have to substitute those factors. Understood? Clear? Normally you don't encounter this in GATE, but in ESC prelims level, some questions they can ask you, and in mains also, of course. Okay, can you get this? If they give you something like these are the kinetic energy correction factors, you don't know where to substitute them, so these are the places where you have to substitute them. Clear? Anyway, let us see what is this kinetic energy correction factor. So kinetic energy correction factor is like kinetic energy rate based on actual velocity. In a detailed course I might have derived this, but right now I'm just giving you the insights of based on average velocity. Based on average velocity, we all know that it is like half m dot u average or v average square is what you have normally per second at a cross section. But here you have to go for certain integration, okay? Because you know, like, let me just give you some quick insight for a pipe at least, so that you can understand something. For a pipe, so let us suppose if this is the cross section of a pipe, okay, at a section, okay, so this is at a section, this is a cross section. So at this section, clearly you know velocity at this point and this point are not same, they are different, but effectively fluid is coming out of this cross section. Let us suppose I have cut a pipeline so that you can see the fluid coming out. Then through this cross section, whatever is the discharge is nothing but m dot is like d m dot is equal to rho u into or v at that, let us suppose at this point, at this radius if I am talking, at this radius if I am talking r, then you know this is like rho into vz into 2 pi r dr is the actual flow. Now if you want kinetic energy of this particular part, dm into vz square, so this gives you rho vz cube 2 pi r dr actually. Okay, now what we'll do, this is actually the kinetic energy passing through this small element per unit time. So if you want the complete kinetic energy, this can be written as alpha is actually equal to integral 0 to capital R rho vz cube into 2 pi r dr divided by, based on average velocity. So based on average, half is also there, okay, because half v square is there, so half kinetic energy is half mv square. So half into total mass flow rate, which is like flow area into discharge into average flow area into average velocity. So density into v average into flow velocity is equal to rho into v average into flow area, which is pi r square. So this is the mass flow rate. Now this is happening at square, okay. So this is the expression. What you will get is, if you substitute this v average in terms of r square by 8 mu minus dp by dz, and here if you keep this vz as r square by 4 mu minus dp by dz 1 minus r square by capital R square, and if you do integration, it's simple integration, single variable integration, but you have to do a lot of you know, maths actually, calculation. So that gives you 2 actually in case of laminar flows, okay. For Huygens-Poiseuille, this integration will actually give you a fixed value, which is 2. Right now I'm not doing, but I don't know whether I have the notes or not right now in the board. Normally in paid batches, in detailed course basically, okay, whenever you have certain long time to do, I would have shown you this integration, but this is simple, you got the idea what to do, correct. In case of v average, you can substitute r square by 8 capital R square by 8 mu into minus dp by dz. Here you can substitute capital R square by 4 mu minus dp by dz into 1 minus small r square by capital R square. And if you do this simplification, it's an integration, single variable integration. If you do, and if you simplify, you will get this value as 2. Similarly here beta integral 0 to capital R rho times vz square into 2 pi r dr by rho times v average square into pi r square. That's it. If you do, you will end up with this value as 4 by 3 for laminar flows, which is 1.3. Beta is 4 by 3 in case of laminar, and this alpha moment kinetic energy correction factor is 2 in this case. Okay, you can tie out these integrations as homework, maybe you know, just a single variable integrations, you can easily do. So this value will turn out to be 4/3 and this value will turn out to be 2 in case of laminar. In turbulent we have certain range which I'll give you the values when we talk about turbulent flows. Clear? So is this clear to all of you? Is this clear to each and every one of you? I'm from batch D, can't access your notes. But actually I taught for English batches actually, okay? So I think you're from English, that's why you cannot access. Anyway, I'm in that loop of taking permission from the people. So if they permit, I'll try to upload my fluid mechanics complete notes for you, okay? So that you can check everything, whatever you want. Okay, so these are a bit of things you have to. Why this is useful is when you are writing Reynolds transport theorem continuity equations, you might have seen we are writing m dot v inlet at x minus m dot v outlet at x, all these things we are writing, okay? Similarly, when fluid is flowing through the pipe at any section, the velocity is not uniform, okay? So there are velocity variations, so to compensate these variations we have to put a beta. That's what. Okay, so anyway, these are the things. Now before going for problems, I think some 15 minutes is left. I think boundary layers I cannot start today also. Guys, I'm planning to take turbo machines on Sunday, okay? Maybe some long class, 2.5 3 hours class I'll take and I'll close in a single shot, okay? But before that we'll try to, because the main thing is normal time would have been sufficient if I haven't taught you the XC part, the Reynolds transport theorem applications. Similarly in boundary layer I'll talk about some important insights of Prandtl-Meyer equations and all, and we'll also talk about potential flows. So I'm planning to discuss these things so that it would be helpful, okay? Because on the thumbnail it's written ME/XC, so we have to justify that somehow. Are you all understanding the things? इवनिंग टाइम ले लो सर, लेकिन इवनिंग टाइम रामानंद सर की क्लास है ना स्ट्रेंथ ऑफ मटेरियल्स, उसके बाद बच्चों का पेड बैचेस भी है. सो अगर मैंने इवनिंग टाइम पे लिया तो जो लोग पेड बैचेस में एनरोल हुआ था उनको थोड़ा दिक्कत हो जाएगा. Okay, are you all understanding things? Are you all understanding fluid mechanics in a different way? Definitely. Are you all feeling this course helpful? Are you all learning some points, logics behind why this, why that, why something is happening? Yeah, okay. So let's, what we are talking, kinetic energy correction factor. This concept of equivalent pipe we'll see. Concept, what is the spelling of concept? Concept, okay, concept of equivalent pipe, yeah, equivalent pipe, concept of equivalent pipe. So what the equivalent pipe concept is actually, look, let us suppose there are two locations between which you have to transport some fluid. This is location A and location B. Now what happens, because of certain physical constraints, you cannot have a pipeline of uniform diameter. Let us suppose here there is some other device, okay? Practically speaking, let us suppose you have made a plan to connect these two by a pipeline, but let us suppose in your plant, let us suppose there is some compressor here, okay? So some compressor, let us suppose you are transporting air, so there is a compressor. This side there is some big space, so there could be certain space constraints where you cannot maintain a pipeline of uniform diameter, okay? So if I would have missed these classes, then definitely I was going to faint. It's okay, yeah, cool. So when you have this pipe of different diameters and different things, actually, then like this, I'm a very bad artist, so please forgive me for my poor drawings, but I hope you can understand the things. Yeah, and you have one more pipeline, let us say something like, so I'm putting only 3 pipes to make you understand the business. Then this is L1 of diameter D1, this is of diameter D2, and this is L2, and this is L3, and this is D3. Okay, so let's suppose you are transporting some fluid. Now what the concept of equivalent pipe is actually, look, you take a pipe of uniform diameter between these things. These are normally called pipes in series, you know. This is a pipe of equivalent diameter, and this is of length same. Length cannot be changed, correct? Because if you want to transport the fluid between two places, definitely the distance between the two places is locked. So okay, now it's fine. Please type in the chat box. Is it fine now? Is it fine? Yeah, clear, right? There was small power typing issue today. I don't know why, but yeah, sorry for this. Okay. And sorry, some questions meanwhile. So can we also expect source and sink flow past bodies? Why not? Yes, definitely. Yeah, that's it. Okay. So what we are talking about equivalent pipe. Okay, so equivalent pipe. Now, if you see equivalent pipe, what is equivalent pipe is a pipe of uniform diameter between same points to have same amount of discharge with same amount of losses. Actually, okay, means whatever is the loss in this plus this, the same should be the loss in this total pipe. Okay, now let's see if the discharge flowing in this pipeline is Q, the discharge that should flow in this pipeline is also Q. Therefore, HL, head loss in this pipe, HL1 plus HL2 plus HL3 and so on, as long as you have. Then what you can do is HL. What is the expression for HL? If you go to the Darcy-Weisbach formula, we have derived something 128 mu QL by pi rho GD power 4, correct? So 128 mu QL by pi rho G D E power 4. Okay, so this is what we have. So this loss should be same as 128 mu Q L1 by pi rho G D1 power 4 plus 128 mu Q L2 by pi rho G D2 power 5, sorry, D2 power 4 plus 128 mu Q L3 by pi rho G D3 power 4 plus and so on is what you have. Now try to understand one thing. The fluid flowing is same in all the pipes, correct? Because it's a series. So whatever fluid flows here, same fluid will flow here. Means in every pipe the dynamic viscosity is same. The same fluid we are also flowing in this pipe. So clearly this 128 by pi is anyhow constant. You can cancel this all over. Then this mu is also constant everywhere. So you can cancel. Okay. Then this density into gravity, again you can cancel. Density into gravity. Q, discharge. Whatever is the discharge flowing here, same is the discharge flowing in all the pipes. So that also can be cancelled actually. So you can see LE by DE is equal to L1 by D1 power 4 plus L2 by D2 power 4 plus and so on plus Ln by Dn power 4 actually is what you're having, correct? This is power 4 again, right? Can you see this equation? Yes or no? So please type in the chat box. Can you see this? Because if all the losses, if you equate, this is power 4, right? Power 4 or power 5? This expression is correct here, rho G D power 4, correct? So if that's 4, then yes, this is also 4. So 128 mu Q L by 4 is what you have. Yes, so this is what you have actually. So in this equation, you can substitute different values of L, and LE is nothing but L1 plus L2 plus L3 and so on. So DE can be calculated using this formula. Correct? Everything is right, because I remember it should be 5 here actually, but how 5 comes actually? Nothing, no? 128 mu q L by pi rho g d power 4. So density is same, everything is same. Correct. This is correct, right? Yeah. Because I suspect that it should be 5 here or 4 here. This 4, correct? Everything is on track, right? Yeah. So this is the equation using which you can calculate DE. Okay. So normally when you have pipes in series, what happens? The losses get summed up. That's it. Okay. So it should be 5, correct? Yeah, that's what I remember. It should be 5 somewhere here. So let's check what we can do to get 5. Because everything is same, the losses wise it's balanced. 128 mu q L. Anything conceptually that we are making mistake here, or something we should do? LE DE power 5. If you multiply DE, L1 D1 by D1 power 5 plus so on. But how 5 is coming? The loss is actually pi j d power 4, correct? Then how come? Can we do something to get 5? Because as far as I remember, there should be 5, correct? But from where the 5 comes actually? Any idea? Yeah, it should be 5, I guess. Even I have this doubt, but from where we can get that? Because the loss is actually in this pipeline, the losses is, this expression is correct, right? We have d square. So when you write 4q by d square, so this is clear. This is correct. We have pi rho g d power 4. This is straight away. Yes? Yes or no? This is 4, correct? From this analysis. From this Navier-Stokes, when whatever you have calculated, this is pi o g d power 4. This is clear. If this is correct, then how come we are getting a 5 there? 128 mu q L, q discharge. So q is discharge, yes. L pi rho g d power 4. What we can do to get one more diameter? Because this has to be valid definitely. The pipe should actually suffer same loss. Okay. So whatever the fluid loss between these 2 points, the same should be the loss here also. And the discharge should be same. So clearly if you do 128 mu q L E by pi rho g. Rho g is common, it can be cancelled. Pi is also common, 128 it can be eliminated. Then q. Discharge should also be same, because whatever flows here, same thing should flow here, and if q is here, then every point it is q. Conceptually there is nothing lock. But how come? I think there should be some small conversion somewhere. Okay. Any idea what we can do to get 5? Because clearly we can see a 4 being present here. HL. What are the other formulas for HL? Let us write it in terms of some other formulas. What we have? HL. So anything? 128 mu q L. This is head loss, correct? By rho g d square. So 32 into 4, 2 4s are 8, 3 4s are 12, correct? Mu q, V average 32 mu V L. Using this only we got this conversion, right? So definitely this is F L V square by 2 GD. Yes, this is correct 100%. So definitely this is also correct. So if this HL is correct, then how do we get a 5 there? 32 FL Q square by 12.1 d power 5. What is this? 1 by 32. V average will be in square, is it? V average is in square here. 32 mu V average, but we have only one V average na here. FL V square FL Q square by 12.1 d power 5. How come? q square. But here we have only q, no? We have only 𝐂𝐸, we have only q here, correct? How you can get q square actually? Achha, if you adjust a q, is what you are telling on the top and bottom? No, I didn't get you. V average will be in square. But here in terms of discharge, you have only one q, correct? You want me to adjust a q on the top and bottom? Is that what you want? And convert the bottom q in terms of diameter? (128 mu QL by pi rho GD power 4). Okay, so it should be 128 FL q square. Is that what you want me to do? Adjustment of a q on the top and bottom. Okay, you want me to adjust in terms of friction factors. Okay, fine. If I write in terms of friction factors, then you have to go for an assumption. You have to go for one more assumption, that friction factor is same in all the pipes. If you make this assumption, then I can do that. Otherwise, I cannot do that. Okay, so friction factor in all the pipes is same. Means basically here F1, F2, all these things should be same actually in that case. Okay, yeah, clear? Q varies in the equivalent pipe. No, Q should be same actually. Q should be same actually. Okay, now let us see. If you write this, if you make this assumption, then definitely FL V square. So what is V square actually in this case? So V is equal to 4Q by pi D square, clear? So V square will be 16 Q square by pi square D power 4. So FL V square by 2 G, one more diameter. Yes, now we are getting D power 5 after making this assumption. Now similarly, then it's done. You can just do a bit of math. F1 L1 16 Q1 square by 2 pi square G D power 5 D1 power 5 plus F2 L2 16 Q2 square by 2 pi square G D2 power 5 plus and so on. Okay, you can write. Now clearly the discharge flowing in all the pipes has to be same. So Q cancels out this Q square all over. 2 pi square is constant in every term. So 2 pi square. Then G is also constant. G is also constant actually. 16 can be eliminated. So 16 if you eliminate, then you have the equation something like FL by LE by DE power 5 is equal to F1 L1 by D1 power 5 plus F2 L2 by D2 power 5 actually plus and so on is what you have. Okay, if you have n pipes, Fn Ln by Dn power 5 actually. Okay, so this is what you have, correct? Is this clear? Because this discharge is actually 4Q by pi D square. So if you replace this FL V square by 16 Q square by pi square D power 4, then this calculation is coming. This is just an assumption. Okay, if you don't have this assumption, then the friction factors will still remain in this equation. You cannot directly get the Dupit's equation. Okay, so only after making this assumption you can calculate the friction factors. If this assumption is not there, then you cannot neglect the friction factors, then the denominator will be 4 actually. Clear? This power will be 4 until and unless you make this assumption. Friction factors is actually same in all the cases. That means basically we are telling Reynolds number is same in all these pipes. Okay, so this is a very powerful assumption actually. Reynolds number is same in all the pipes. This, in other words, you can say this V average into D product is maintained same. That's what. Okay, so anyway, if you make this assumption, then clearly this F gets cancelled. Then you have the Dupit's, of course. LE by DE power 5 is equal to L1 by D1 power 5 plus L2 by D2 power 5 and so on plus Ln by Dn power 5 is what you have. Okay, so you can write this LE by DE power 5 as summation I equal to 1 to n LI by DI power 5 actually. Okay, so this is what we have. This equation is given by Dupitz actually. Okay, but actually this assumption is like very practically it's very difficult to make this assumption. Okay, because fitting Reynolds number same in all these pipelines is not very easy. Okay, because you have to design that pipes in such a way that this product, because Reynolds number at any case is basically F is equal to 64 by RE, you know this. So 64 is anyhow constant. So 64 is anyhow constant. To make this Reynolds number constant, Reynolds number is rho V average D by mu. Okay, and anyhow these guys remain constant. Okay, so these guys remain constants. So V average into D is what you have to make constant in every pipe, which is adjusting V average into diameter as constant is not a easy job actually. Okay, because discharge has to be same in every pipe. Okay, clear? So anyway, we will, I thought of starting boundary layer also today, but I think it's not done. We'll solve one question at least to make understand of the things. Let us solve this question. After solving this question, we'll wind up the session. So let us solve. A frictionless incompressible steady flow field is given by velocity vector is equal to 2xy I cap minus y square j cap in arbitrary units. Okay, so V is given as 2xy I minus y square j. Let the density be rho naught, which is constant. So density is equal to rho naught constant. Neglect gravity, so body force can be neglected. The expression for the pressure gradient in the x direction. Okay, so in the x direction, what is the pressure gradient? So what are the, they have given you certain options. Okay, so if they give you certain options, then what you can do, you know, momentum equation minus del P plus mu del square V is equal to rho into dV by dt. Correct? So this is what you have. Then clearly this is 0 because frictionless, there is no viscosity. They have asked you to neglect this. So in x direction, if you apply minus del P by del x is equal to rho into acceleration in x direction dou u by dou t plus u into dou u by dou x plus v into dou u by dou y actually. Okay, so let us see, this is 0 because they have given you it's a steady. Okay, so it's a steady flow. So dou p by dou x is equal to minus density is rho naught u into dou e by dou x. U is 2xy, x component of velocity is 2xy into dou u by dou x. So this is 2y plus v. So what is v? Minus y square into dou u by dou y. So 2x. So this is like minus, this is 4xy square minus 2xy square. So this is rho naught. So minus dou p by dou x, or dou p by dou x is equal to minus rho naught times 2. This is 4 minus 2 is 2. So 2xy square is what we have. Okay, so minus rho naught into 2xy square, which is in option D. Okay, so clearly normally in case of xy, if you go in the positive direction, this is positive, so pressure gradient is negative, flow is happening. Okay, so simple Navier-Stokes assumption, all these things can give you. Okay, fine. So we'll stop this lecture here. I have left some questions here which act as a good homework for you. So this is one more such question, which is a nice question. Then after some questions to flow through pipes, some losses. Okay, this is a boundary layer question actually, which I'll maybe deal tomorrow. Okay, because the time is up. So today we have talked about a lot of things. Flow through pipes completely we have talked using Navier-Stokes equations. Okay, so anyway, so we have talked about plane Poiseuille and Hagen-Poiseuille, which is actually flow through pipes. Flow through pipe is what you have. Okay, guys, actually we have 2 more lectures as per planned schedule, but I'll want to take one thing in excess as well. Okay, pipes in parallel. Okay, so pipes in parallel, you can see Fine. Okay, I'll show you pipes in parallel. In case of pipes in parallel, what happens is, if you branch your pipe, for example, okay, so let us say let us suppose you are branching your pipe into two parts. For the flow to happen, for flow to be continuous, if the losses here is HL1 and the losses here is HL2, then definitely HL1 should be equal to HL2. The reason for this is, if these two are not equal, then either only this fluid will go effectively and this fluid will stop, or if this fluid goes effectively, this will stop if these two are not equal. The reason is, what is the energy of the fluid particle here? After suffering some loss, the fluid particle will have some energy here. This is some other particle. After suffering a loss of HL2, this particle reaches here. If there is some energy difference between these two particles, either in terms of pressure or in terms of kinetic head, definitely potential nothing can happen. So after suffering some loss, if there is some, let us suppose if the pressure at this location is high, this pressure at this point will not allow very freeness for this point. It's like two lines going and merging in a single path. You know, let us suppose if people stand in two different lines, and if the pressure at this location is high, if they are pushing these guys, then these guys will not be able to move inside. Same logic, because of the pressure, this fluid will not enter if the energy difference is, if the energy difference is large. Similarly, if the kinetic energy is varied, if the kinetic head is different, then also this fluid will try to move effectively as compared to this fluid. So comparatively, the fluid actually blocks and it acts as like a almost single pipeline. Okay, so that's why, in order to not have this losses should be same in all the parallel circuits. Clear? Normally, this concept is very much important for civil engineers. Actually, they have this concept called pipe networks, okay, which is generally dealt by civil. So this pipe networks is not in mechanical, neither in 𝐂𝐸, so I'm not teaching it right now. But actually, how to design a pipe, the optimum path, like how you do in operations research, the optimum path of a process. Similarly, they'll design an optimum pipeline. Inclined, if you neglect gravity, same is the story even for inclined. Okay, there only one difference is, in Bernoulli's equation, when I'm talking about 𝐁𝐚𝐿 I have solved, excuse me, we talk about this head which is called the piezometric. There we deal in terms of piezometric heads. That's it. If you do the same pipeline analysis using this part, even though in this case, since the pressure is the only force, which is where the body force is not much predominant, you will neglect gravity even in this analysis. Okay, analysis remains same, whether pipe is inclined or flat or anything, as long as you neglect gravitational effects on the kinematics. Okay, not on the specific weight and all, on the kinematics, as long as you neglect gravity, the same case. Whatever may be the inclination of the pipe, you deal same things. Okay, but if you talk about hydrostatics part, you will go for piezometrics. Okay, so fine then. So that's all for today. We'll see in tomorrow's class. We'll start boundary layers, and because I thought of starting it today itself, but flow through pipes has taken some time in calculating friction factors and all the showing you all the things. But anyway, tomorrow we'll try to finish boundary layers and all. Boundary layers is generally for gate, it is actually a short thing. Okay, so but anyway, it is really important to understand certain boundary layers. So maximum possible, tomorrow I'll try to cover boundary layers and also dimensional analysis. Okay, then after the last class we will see a bit of turbulence and potential flows. Guys, actually I had a discussion with Vinod 𝐁𝐚𝐿 sir. Normally applied thermodynamics is taught by Vinod sir. So if he teaches, because there's no time, so otherwise I would have taught you compressible flows also. So but compressible flows, if time is not permitted, I'll ask Vinod sir to take, or else if Vinod sir, normally we exchange the things sometimes, okay, because depending on the time available for the subject. So if I cannot teach compressible flows due to time constraint, I'll ask Vinod sir to take it. Okay, normally in compressible flows we have certain nice things to look. Okay, why rocket nozzles are diverging. Normally you expect a converging nozzle to accelerate a fluid, but there could be times where a converging nozzle can actually decelerate the flow, or a diverging passes can actually accelerate the flow. There could be a lot of things like this which we will see. Okay, are you all liking the sessions? Okay, liking means not the like button I'm talking. Are you all understanding the things? Are you all enjoying the sessions? Okay, fine then. So we'll meet tomorrow at 7:30 a.m. again, and we will focus on things. Okay, tomorrow straight away we'll start boundary layers. Meanwhile, you please solve the questions in this notes. Okay, they are easy questions, pretty much you can go through. Okay, so thank you all. Yeah, take care. Bye.